So in the last lecture, what we were discussing is solving the discrete systems using differential equations, or basically what we call in this particular discrete time system is difference equation. And we saw that when we solve for the for the output y, which is basically the sum of the homogeneous solution or natural response plus the forced solution or the particular solution. So both these terms are same, and both these terms are same actually. If you say natural response is same as homogeneous response, or forced response is same as particular solution. So we were seeing this, and then we saw that and then we focused on solving the homogeneous solution first, and thought of doing the particular solution later. So in case of homogeneous solution, you saw that if you do all these type of if you do substitutions like the one which I have explained earlier, you get some characteristic equation here, and solving this characteristic equation, you will have roots of this characteristic equation, and depending upon the types of roots, whether they are real and distinct, or complex or repeated roots, we have different solutions, which is like this one. For the complex roots, we have this one, and for the repeated solutions, we have this one. And these two are equivalent forms, can be represented in either of the way. So these two are the equivalent forms for the complex numbers. If you have complex numbers as the solution for the characteristic root equation. So at that time we stopped here, and so now what I will do is I will give you some simple examples to solve, so that you get to know what's going on in case of discrete time. So if you have these three questions, I'll give it to you for a second to solve. So this is the first one. If you have to solve the homogeneous solution for these discrete type equations, then how will you do that? This is the first equation, and here is the initial conditions for it. So I do not want the exact solution, just give me how will you solve this, like what will be the roots of these equations and all that. So you can uh, we can discuss this then. So we have this as the second question, and the third is yn minus 5 by 6 yn minus 1 plus 1 by 6 yn minus 2 equal to 0, and y minus 1 is equal to 19. 5 minus 2 is equal to 53. So you have these three questions. I'll give you 5-6 minutes to just give me a rough idea of like what kind of roots it has, and then you know how to calculate the unknown coefficients from these initial conditions. Okay, so the thing is, as you know, this is quite similar to what we have done in case of the discrete time. Oh, sorry, in continuous time. But let me show you one example so that you'll get to know what's going on here. Then the other two will be in on the similar, form. So what I will tell, what we know is, like, you will replace all these yns by the corresponding no, sorry, not yns. I told you this thing, right? Here we have these substitutions that we are doing. Yes, with yns, all these yns will be replaced by the z to the power minus k's. So if you do that, then it will be like this. So this will be 1, then 1.4 z to the power minus 1 plus 0.85 z to the power minus 2 equal to 0. Now you can just rearrange these terms of the z, and what you can get after this is, like, because these are all in negative power, so you can bring it into the positive powers, so it will be like this. And so this is the characteristic equation of this particular difference equation. And then what you can do is you can solve this. So what you will get is you will get two roots that are complex. So you will get something like this here. So these are the two complex roots, and you can write it in polar form. So if you write it in polar form, you will get something like this. So this will be in your polar form, and now this term, this term here, actually is as I told you in the last class, this term here is basically R. So if you see the solution to the complex numbers, so what you have is this particular solution, right? This one, and you know what is the value of R now. So the value of R now here is 0.922, and the corresponding value of frequency here, the angular frequency omega 1 will be 0.7086. So now if you substitute these values from the solution of the complex number that you got, then what you will get is this one, yn as d1 0.922 to the power n cos 0.7086 n plus d2 0.922 n, sorry, 922 to the power n sine 0.7086 n. So no, please note that this thing will be like this. I was not writing it in that fashion, but it has to be written like this. So once you have this, now it's very easy, right? You have to only solve for the values of d1 and d2, and you already know these two initial conditions, which are y minus 1 is equal to 5 and y minus 2 is equal to 7. So once you put these initial conditions, and you can solve it for the d1 and d2s, and the value of d1 and d2 that will come out by solving this will be 1.05, and d2 will be minus 5.8583. You can check it at home when you solve this. So once you have these values, it's straight and simple. You just substitute it into these in this solution, and what you will get is the complete homogeneous solution for the or the natural response for the yn. So in this way you have to solve questions related to the uh, difference equation related to discrete time. So any questions here?
Sir,
Yes.
during the differential equation, like suppose you are solving a differential equation, we assume that uh, y of t is e raised to c into e raised to s. So
Yes,
in
yes.
this case, what are we assuming? Y
See,
of
I told you last time, right? This one is this one, right? We are assuming it to be this one. C z to the power n here, we are assuming that our solution is c z to the power n, like this. We are assuming a solution, and then we are substituting this solution into the difference equation. Not c to the z to the power n. It will be z to the power n that we are substituting here in this. So here, if you see, we are assuming that way. See, this is if you compare this, since it's a discrete time, right? So we are using z. So later on we will see that this z is actually the z transform that we are actually we will be looking into. And in case of the continuous time, we were assuming e to the power st, and you can correlate it with the Laplace transform that you will be discussing in the we will be discussing in the next lectures coming. So some way or the other, they have direct link with the Laplace transform and the Z transform in the later chapters. Okay.
sir, we
So
are
yeah,
not like we not supposed to put a constant variable for this?
that will be assimilated in this AK. It can be consumed within this coefficient, and then it will be a modified coefficient. So some way or the other, we are taking AK. Okay. Okay. So if this is done, then what you can do is you can take it for this difference equation here, and the corresponding solution that you will get for this is, you will get a repeated roots. So in this case what you will get is z1 equal to z2 equal to zero point 0.8. So it's a repeated root that you will get for this difference equation, and then if you solve for this, you know that for the repeated root of the multiplicity of order 2, then the solution will be like this. It will be of this form. And then what you have to do now is you have to actually solve for these coefficients, unknown coefficients, which you can do easily by substituting these difference equations. Like, these are the boundary conditions from where you can get the values of these coefficients. So this particular example was for the case of repeated multiplicity. This you can solve yourself. It's very easy. I don't know the solution of this, but you can solve it. There is no, I think there is no challenging thing here once you are exposed to these two type of difference equations. Okay, so now once this is completed, in case of forced responses, also we will have a similar treatment as in case of it was for the continuous time. So if you have a constant, in case of forced response, it depends upon the output, depends upon the type of input that you are feeding. So if the input is of type K, which is a constant, then what you will assume as a solution for that, which is, which you are calling as a particular solution for the complete particular solution for the output YPT. So if your input is K, then you assume the solution to be K1. If your input is exponential, then you assume the solution to be this. If the input is a cosine function, then what you assume is this is similar to what we had done for the continuous time. So it will be like this. And if your input is again, sine omega naught n, then your solution will also be same. And if it is a polynomial, then it will be like this. So this is similar to the one which we had done earlier, right? In continuous time, nothing different. So these are the responses that you will assume in case you have these type of inputs. And we saw earlier also, like, if you want to calculate the impulse response, how we did it, because this impulse response is not available in this table. If you recall earlier, in case of the continuous time, we asked you to calculate the impulse response for the differential equation, and at that time, when you look back into this table, you were not able to find anything related to impulse response. But then we observed that the impulse response is the derivative of the unit step. So we took this particular solution and then took the derivative of the response that we got for the unit step. So when you take that, and you assume that the derivative is a linear operator so that it can move inside the system. So based on that assumption, you got the response for the impulse by taking the derivative of the unit step response. So that has to be kept in mind here also. Like if I ask you to calculate the impulse response, then you have to do in that way. So let us say, and also you note that if you are calculating the impulse response and if the initial conditions are not given to you, then the automatically it has to come into your mind that impulse response is normally for linear time invariant systems. And if it is the case, that is, if it is for linear time invariant systems, the initial conditions corresponding to that will be 0. This is very important. So if the linear time invariance is coming into the differential equation, then you have to automatically assume that your initial conditions are 0. We have proved it in case of continuous time system. Same thing applies for the discrete time. Okay, so if you have this question, let us say yn equal to 1 minus alpha yn minus 1 plus alpha xn with xn as unit step, and your y minus 1 is equal to 2.5. So if this is the question that is available to you, I want to know the forced a complete response of this system. So I'll give you five minutes to solve it because it's not that difficult in terms of the computation. So right now 8:25, I'll give you 5 minutes, like 8:30. Just let me know what is the answer to this. A complete response, which is YHN, that is the homogeneous solution, and the particular solution for this difference equation. Okay, Varun, what was your answer? Okay, Varun, what was your answer?
I even solved it further, so it's 2 upon 3 whole raised to n.
2 upon 3 whole raised to the
Whole
power
raised
n.
to n. Now
Hmm,
integrally plus 1. Like integer में plus 1.
like
No, no,
this.
no.
Okay, okay.
Not on the power.
Like this. So this is your answer. Where was 1 minus alpha?
Sir,
Which you,
I actually solved it using the initial condition.
no, but even if you solve initial condition, the value of alpha will all value of alpha you cannot solve. It will be there within the expression.
Okay, so there might be like 1 minus alpha whole raised to n plus 1. Like instead
Yes.
of 2 upon 3.
So something like this. The answer is actually 1.5, not 2 upon 3. I think it's 3 upon 2.
Okay.
So then it is 1 minus alpha to the power n plus 1 plus 1. Something like this. This is your answer. So this is simple actually. You can solve it yourself also. Like what you will use is you will assume the homogeneous solution as c to the power z c z n, and then based on this, once you put this into the expression for this, assuming your input is 0, then this is gone, and then what you can get is as a homogeneous solution will be c1 minus alpha to the power n. This is your homogeneous solution once you put that. And for the unit step, what you are doing is you are assuming a particular solution ypn as k1. This is your assumption for this because we know that a unit step will have this as the solution. And then what you do is you put this ypn k1, which is equal to k1 here, into this expression, and then you can easily solve for the value of k, or you can say k1. You can easily solve for that, and the value of k1 will come out to be 1 as you substitute this ypn as a solution, right? So you can put easily here, it's a constant, so the solution will be like k equal to 1 minus alpha times k plus alpha. So when you solve this, what you will get as the answer is k equal to 1, and then you can easily substitute it with the homogeneous solution that you have here, which is c 1 minus alpha to the power n plus 1 equal to the total solution that you have here, yn. And based on the initial conditions, like if you put y equal to minus 1 here, that is 2.5, then you can get the answer for this corresponding c here. And once you get that value of c, you can substitute it back into this expression to get the total response of this difference equation. And the value of c that you will get here will be 1.5 times 1 minus alpha. So once you put that and plug it here in this equation, what you will get as the answer is this. So you can solve these type of questions, like how to do it. So this basically finishes off the difference equation. So now I'll just switch gears and be a little bit fast because I have to complete this particular topics related to discrete time system today itself. So in block diagrams, we discussed in detail the block diagrams for the continuous time systems. So the same thing is for the difference equations also. So if you have a difference equation which is like this, so if you do like this, you have this difference equation, and then you have b0 xn plus b1 xn minus 1 plus, you will go like this. So I'm currently taking only three terms, so there is no dot here. So Similarly for here also you will have like b0, b1, b2, x n minus 2. So this is if you have this difference equation, let us say taking a particular specific terms like on the left and to the right. So if this is a difference equation, the corresponding block diagram that you can obtain is similar to what we had done for the continuous time system, in which what you had done was you replaced initially yns by w's. So if you do that, the left hand side will become like this, that is xn equal to wn plus a1 wn minus 1 plus a2 wn minus 2 plus a3 wn minus 3. And then what you have to do is another step is to to write yn equal to this expression on the right side but replacing x by w's. So what you get here is b0 wn plus b1 wn minus 1 plus b2 wn minus 2. So if you do that, then you can easily write this in the form of block diagrams, and that is like you will have something like this. So it is xn here, then we have a plus sign, and then what you get here as the output is, let us say, wn. Then you have a difference equation d, which actually takes the difference between the two, wn and wn minus 1. So this is basically a sort of delaying operator. So it delays what is fed into the input to this block. So if it delays by this by a unit of 1, then it is wn minus 1. So that means if you are putting a d operator, means you are actually delaying the samples by 1 unit. If you do again, then it delays the samples by 2 units, and then again delay, then it will give you a sample by 3 units. So these are the three uh, terms that you will get, because you are actually working till n minus 3. So you will have 3 delay units like this, and from here you can you can put the coefficients like the way we have done earlier. So here you can tap this line, multiply with the coefficient minus a1 and add it here. You can tap this line, multiply it with coefficient minus a2 and join here. And same for wn minus 3, you can take this, multiply it with minus a3 and join it here. So this particular block is actually representing this expression which is over here. Now for this, what you have to do is you have to take b0 out. So from here, if I take b0 out, so you multiply it by b0, take outside, you take multiply b1 with the wn minus 1, take this outside, and you take multiplication of b2 with wn minus 2, take this outside, and once you have these three, you can add it together to get the answer as yn. So this is basically the block diagram in case of discrete time systems. So again, a point to be noted here is that if you have initial conditions along with this, as we had discussed in continuous time in a very much detail, if you recall that, if you have initial conditions here also, then the initial conditions will be in the form of like this, like you'll have y minus 1 equal to, let us say, 2, then you have y minus 2 equal to 3, like this you have some initial conditions, or y plus 2 equal to, oh sorry, not plus 2, it will be minus only. So whatever initial conditions that you will have here, what important thing is, in case of these initial conditions for this particular difference equation, what you have to do is you have to convert this into the initial conditions related to the parameter w, as we had done in our continuous time system. So you have to come up with the initial conditions like w minus 1, w minus 2. You have to convert these variables y into w with these initial conditions. So you have to actually solve for that, as we had done in case of continuous time systems. So I am giving you one question, so you can solve it. Maybe in the next class you can tell me the answer. So if you want to construct the block diagram for this particular system, what will be the block diagram? You can show it to me in the next class. So this is basically the question. So in this, what you have to do is you have to actually construct the block diagram as we have discussed here. So it's just, you have to draw this block diagram here. So for this particular difference equation, but the only thing now is that in your xn is equal to un here, y minus 1 is equal to 0.5, y minus 2 is equal to 0.3, y minus 3 is equal to minus 0.4. So these three initial conditions are there. So what you have to do is, you have to actually, along with solving this block diagram, along with solving this difference equation, you have to actually convert these difference equation initial conditions into w minus 1, and you have to tell me what that value will be, w minus 2 and w minus 3. So you have to tell how you can move from y to w and what are the values. So it is nothing but just substitution of the variables here and there and solve for the answers. So once you have this w minus 1, w minus 2, w minus 3 initial conditions, and then using these initial conditions along with this block diagram, you can have a complete difference equation corresponding a complete block diagram representation for this particular difference equation along with the initial condition. So if you have any questions here, you can ask related to this, but it is very similar to the details that we had already covered in continuous time. Okay, so once this is done, the convolution also follows the same route. So in convolution, convolutions normally, in case of discrete time will be, it's k minus infinity to infinity. It will be xk hn minus k. So you can see there is a lot of similarity here, but the only difference that lies is that, you have a discrete time system instead of the continuous time systems. So, but other than that, everything is same. So you have to keep in mind that how to plot these discrete time systems, because in some situations what happens is, for example, if you have, let us say, if I tell you xn is un minus 1, un minus 7, if I tell you this, so how many samples it will have? Can anybody tell me how many discrete samples it will have if you do this? Anyone?
Seven.
No. So that is the catch actually. That's why I wanted to discuss this. Uh, Actually, it is not 7 samples here. It will be like, yeah, yeah, you are right. It will be 7 actually. But can you tell me the indexing, like from where it will be?
Zero
Yeah.
to six.
Yes, right. So, yeah, yeah, right. So that's what I wanted to point out, that it will not be the 7th sample here, because ultimately, the 7th sample gets subtracted from the 7th sample of the UN. So it will be from 0 to 6. So if you include 0, so it will be 7. So it will be up to 6, not 7. So that is important point. So you have to take in care, like when you do or handle the discrete time sequences, you have to see which sample is getting subtracted out. In continuous time, sometimes it's not that big deal. So, but other than that, normally what happens is, it's solving this is similar to solving geometric progression. So once you have these sequences, like if you have these sequences, like this thing, this is up to 7, let us say, and if I want to convolve this with the exponential function which is 0.9 to the power n un, let us say. So if this is your hn, let us say, then you know that if you plot hn minus k, it will be something like this, something like this. So this particular sample at this point will be having an index of n. However, this running sample, this time index is k. So you know that this is your xk. So you know that if your n is less than 0, there will be no overlapping, and if n is greater than 0, they will start overlapping. And you know that this is a finite sequence. So you have three ranges here. One is n less than 0, another one will be n greater than 0 and less than 6, and the third one will be n greater than 6. So these three, in these three ranges, you can solve for this difference equation and you can get the answer. So this is very easy, and there is no, there is nothing, details required for this. So I think it's you can solve this by substituting these values into this particular expression and changing the limits k here as per the limits that you will get here for the discussion that we are doing. And the important thing is, this all the examples related to the discrete sequences will be reduced to geometric progression, and you can solve it using the general terms related to that. So this actually finishes off with the treatment of all the systems and the signals and all the related properties of that. In the next chapter or in the next lecture, what we will discuss is we will discuss the Fourier series analysis for the signals and systems. So if you have any questions now, you can discuss. Otherwise, we can leave the class. Okay. So thank you. We'll meet next time. Yes. Midsem exam will be somewhere around, maybe next week or next to next week. It will be in mid of it. Okay, because this complete semester which I have seen was around of 8 weeks, right? So I'm planning to put it on, on mid of this fourth week, like, once this week will finish off, or maybe at the starting or mid of the fifth week, something like that. Okay. And the important thing is it will be conducted here only. So what you have to do is you have to open your computer screens, and we will be taking exams on this. There will be no metal exam for this particular thing. So we will give you questions, and the thing is you have to scan the copies and upload it onto the system so that we can check later on. So it will be on your own copies. Okay. So that's it. If you have any other questions, you can ask. Okay. Okay. Thank you. Then we'll meet tomorrow.